Happy New Year.
We are starting a new unit. So that quiz was actually the end of that unit with cube roots and square roots and all that goodness. We're moving on. We're going to go to piecewise functions. Okay, so we're going to be able to evaluate and graph them today. Let's make sure we know what it is. So looking at this, that's an example. What do you think a piecewise function is?
It's a function and it looks like a piece.
Yeah, it's pieces of different functions. What pieces do you think I used here of different kinds of functions? I used a piece of a parabola and a piece of a line. All right, what else do you see happening on this piecewise? What you see, Adam?
They don't meet up.
They don't meet up. There's a little gap. Yeah. What else do you see?
There doesn't pass the vertical line fence. No, I don't know why I said that.
It does because of something else that's there.
The circle.
The circles, right? We see an open and closed dot,
Oh.
right? There's a gap. What do you see at the ends for this one? There's arrows at the end of this guy. Sometimes there's arrows, sometimes there's not arrows. So make sure you always pay attention to beginning and end because it'll switch up on you. Okay? So these are two pieces. One is a parabola, one is a line. Where did the parabola stop? Where x equals what?
3.
Where did the line start? Where x equals 3. Because one was closed and one was open, this one is a function because your x value of 3 is only being used the one time on the parabola. Okay? If they were both closed, that would be an issue, right? Because then your x value is being used in two different functions. You can't have that. What if they were both open? Is your x value being used twice if they're both open? No, it's actually not being used at all. So that's okay also. So the thing you cannot have two closed pieces on the same x. Anything else is fine. You okay? You sure? Okay. We good?
Yeah.
All right. A piecewise defined function is made up of defined functions based off of rules of the domain. What's our domain? Remember this word. It's your x's. Isn't that where one started, or one stopped and one started on the last thing? The domain is the rules. It tells you where they live. Okay? If I have x right here, x squared minus 3 and 3x minus 2. Okay? Can they exist on the same graph and it stay a function?
What did you say?
Can these two exist on the exact same graph and it still be a function?
No.
If they're both on there.
Yeah, because they're different. No.
But
They're not.
I have x's being used more than once, don't I? So putting them on the same graph is not allowed if I want to keep it a function. Okay? That's what the domain does to help me keep it a function. This is how your piecewise functions are written for you. It gives you the functions and then it gives you the rules. So x squared minus 3, my parabola, it's only on there when the x's are what? When they're less than or equal to 0. So that means the right half of the parabola does not exist on the graph. Only the left-hand side, right? Only when the x's on the parabola are less than or equal to 0. Which means I get to give this an open or closed dot. Equal to, yeah.
That one.
Okay. And then the other one is when x is greater than 0, right? So my line only exists on this graph if its x's are bigger than 0. So I need to get rid of the other side. And this one gets an open circle. That's how we're getting our two pieces. It's telling you where it can exist so it can remain a function. That's the whole point of the rules. Okay? So we're going to use it. So we're going to actually graph it. On your big graph on the side, you're going to put the pieces on there that you need. So your parabola, it got shifted down 2, right? I mean down 3, excuse me. X squared minus 3. So it got shifted down 3, that's your vertex. If I'm only doing the left-hand side of that graph, what can I do? What pattern? 1, 3, 5. Good, but we're only going to do it on that one side when x's are less than 0. We're going to get more into graphing them tomorrow. We're just kind of doing a sketch right now, and then we're keeping it easy. We'll get fancier with graphs tomorrow. And then my line only exists afterwards, so it starts at the y-intercept at -2, and then it continues that slope of up 3/1. That's how you should be graphing it on your paper. Don't forget for your closed and open pieces. If you want to graph like the whole parabola and then erase the half you don't need, you can do that. If you want to graph the whole line and then erase the piece you don't need, you can do that. Again, we're just doing a rough sketch today. We're going to do a whole lot more graphing tomorrow. Today is more, can we interpret the graph that we're given? Okay, but we're starting simple. Okay, so we're going to call the parabola the A interval, and we're going to call the line the B interval. So when it's asking you about A and B, that's what it's referring to. The domain of the piecewise graph can be represented with intervals. We can define interval A as x is less than or equal to 0. What can we define the interval of B? What's its domain? X is greater than 0. Yep. My next 2 blanks are asking us about increase or decrease is what we're going to talk about in the next sentence. So when we read a graph, it's like reading a book. We go left to right. Okay? So as we move over my graph, starting at the left, moving over to the right. Interval A, would you say it's increasing or decreasing? It's decreasing. And then as we move on, interval B is increasing. Read left to right. If I were drawing it, I would fall down first, and then my pencil would go up. All right, the graph is nonlinear or curved when the domain is what? Which domain gives me the curved part? My domains are going to be x is less than or equal to 0 or x is bigger than 0. So which of those domains gives me the x squared part? X is less than or equal to 0. Oh. So where is it curved? If the x is less than 0, it's part of the curved graph. All right. And then vice versa, the graph is linear when my domain is what? Where is it aligned? When it's greater than 0. Can it be equal to 0 and be part of the line? No, it can only be bigger than 0. These next 2 paragraphs I feel like we already talked about. So the closed circle is where we are including the 0. Was less than or equal to. The open circle is when we are not including the 0, and that was illustrated in x is greater than 0. So I feel like we've spoken about that a lot out loud. We just haven't written it down yet. So closed circle included, open circle not included.
Oh, shoot.
You okay? Oh, here, I can fix it. Mine has a little wheel. And you can like. I don't know if I can. No, mine has like the wheel that I can actually like turn and bring it back. Those are my favorite. All right, discontinuous and continuous. Something else you've probably heard of before, but it might have been like one day in Algebra 1 that you might not fully remember what it was. So a discontinuous graph, is when there is broken pieces or holes in my graph. Okay? Continuous, there's no holes and there's no breaks. So looking at the first graph, would we say that that is a continuous graph, the first one? No, why not?
Because it's 3 parts and it's all broken.
So the 3 different pieces is okay. The issue is they're broken. Okay? They're 3 broken pieces. And I see holes in the middle. So that is not continuous. All right, would I say that the middle one is continuous? Yes, that one's fine. There's 2 pieces, but they meet at a solid point, right? So that means it's included. So we're including all my values. All right, is the last one continuous?
No.
No, why not? They're all connected,
It's had an open dot.
but they got holes. Yep. If you have holes or breaks, cannot be included.
So it can't be an open dot?
Nope. That's a hole. It's a hole in your graph. There's a way to actually type in your calculators and it'll show you holes and breaks. Pretty neat. We go, but remember continuous, discontinuous? Maybe. Okay, here we go. Let's look at this guy. We have 2 pieces, right? We have a curved piece. We have a straight piece. What is the domain of the non-linear piece of this graph? X is less than 1. Y'all agree with Kaylee? Good. How come she did not say less than or equal to?
Because it's an open dot.
It's an open dot. Good. This is when all the x's are less than 1, that is referring to the curved piece. All right, what's the domain of the linear piece? Greater than or equal to 1. Good. So the other side is going to be my line.
Yeah, that's where it's
1 is the x that they're meeting at. So they're both starting to stop right there. Yeah, you got it.
So if it's negative, they're less than. And if it's going up, it's
What?
for you said x1 is greater than x because it's decreasing.
Nope, it's actually just talking about the pieces of the line. Or do you mean it's decreasing from the 1, like it's moving to it's on the left side of the 1?
Down.
It's not about the graph going down, it's on the left side of the dot.
Oh, it's like that shaded thing.
Yeah. Okay. All right, the range of my function. Haven't done this yet. So what values am I looking at now? The y's. Well, I have 2 arrows pointing up, so I can't be all real. Right? That's out. Even if my arrows, by the way, were pointing opposite directions, if there's a big old gap in the middle, it's still not going to be all real. So make sure you pay attention. Okay? But my first clue here is they're both pointing up, so all real is out. So what is the lowest y value that this graph goes?
3.
And then how tall is it going to go? Infinity. There is a little gap in between, right? But those y's still exist. They're just over there on the line. They're not on the curve. Does that make sense? So the y's are there. It's not asking what piece. It's actually asking about the whole function. So all these y's are bigger than or equal to 3. All right, is this piecewise a function? Yes? How do we know? Our vertical line test, yes. But what about that part where I get to the 2 dots? Good. One of them's open, so we're good to go.
What's the vertical line test?
So you take a vertical line, like your pencil or your finger, and you move across the graph left to right. You make sure the actual graph does not touch that vertical line more than once at a time. Remember my parabolas, when they got turned to their side, they didn't pass it anymore. So if I try to do a vertical line right now, I would be touching my arms twice. Does that make sense? That's why. All right, is this continuous? No, why not? There's a hole, there's a break, there's a gap where we at x equals 1. Okay, so those are my,
Wait,
what?
one of them is filled in. Why is there a gap?
So you're thinking, so the vertical line test is fine. but there is a gap between the two functions. The functions don't connect, so it's not continuous. Yep.
Isn't the open circle thing? Is why.
Because there's a hole and there's a physical break, so my
Yeah.
functions don't actually connect to each other.
Widespread.
Yep. All right, so we're done with graphs. We're gonna move on to functions now. Okay. So I'll either give you a graph or I'll give you a function. Now we're gonna evaluate. Okay. We're gonna figure out where he lives and then we're gonna take him home. That's what we're gonna do. Okay. So if I have this new function, negative x plus 5 and x squared plus 2. Okay. On my graph, I would only graph the line negative x plus 5 between the x values of 0 and 6, right? Starting and ending with open dots. See how I see that? Okay. I don't have to actually do it. My parabola of x squared plus 2, I would only graph that on a graph if the x's were bigger than or equal to 6, starting with a solid dot. So can you just kind of visualize it a little bit? We have a negative line. I guess for you guys it would go this way, right? Open to open. And then from there would be a parabola going off to the side. Okay? F of 2. I have changed my x to a 2. Where does 2 live? Does he live on the line or does he live in the quadratic? Where is 2 going to fit? Is it between 0 and 6 or is it bigger than 6?
It's on the line.
It's between 0 and 6, right? So we know where 2 lives, so now put him in his house. So that's the function you're going to plug it into. You're only going to plug it into one of them. Okay? He only follows the rules to live on the line. So we're going to plug it into negative x plus 5, so negative 2 plus 5, which gives us 3.
That's it?
Yes. So you've evaluated before. You're very good at it. We're just adding like a little puzzle piece in the beginning. You have to figure out which one you're going to plug it into first. So 6, where does 6 live? On the line or on the parabola?
Parabola.
On the parabola, because we're equal to 6, right? On the parabola. So we're going to plug it in to x squared plus 2. Gives me 6 squared plus 2, which is 38. All right, now we have f of 8.
Also on the parabola.
Also on the parabola. Good. Plug it into x squared plus 2, and we're going to get 66.
How do you know which one?
You have to figure out which rule it follows. So the x of 2, is that x in between 0 and 6, or is that x bigger than 6? So you figure out which rule it follows. So 2 is in between 0 and 6, right? So I'm going to take 2 and plug it in to negative x plus 5.
This next one doesn't go into either.
Okay. I don't have any more. Oh, on your paper. That's going to be a new function.
Oh, okay.
I was like, what? F of 6, by the way. It was special. How was it kind of special? Because it was on both, right? But it only plugs into the first one. That actually shows you where the parabola is going to start. So like if I were to graph the start of my parabola, it would be at the point 638. That's where the parabola starts. To figure out where the line ends, you could plug in 6. So the line is going to stop at negative 6 plus 5, which is negative 1. What's up?
Why did you do the first rule for the f of 2, but then the second rule for the next one?
Because 6 is equal to 6. So that's going to go into the second parabola, the second function. My first one is in between 0 and 6, not equal to 6. So x equaling 6 does not fit right there.
Okay.
That would not make a true statement. If I replace this x with the 6, that makes a true statement. And then 8, again at the top, 8's not in between 0 and 6. So here, 8 is bigger than 6. Yep. Okay. Any more questions about evaluating?
No.
Okay. If you have not already, I want you to start these next ones. You try these. I'm going to go with Hannah. F of negative 7. What rule did it make true? The first one. Good. So we plug it into negative 3x plus 2, and that gave you what? 23. Good. I will let you popcorn to somebody else. Idri, how about f of 3? What rule does it make true?
The second.
The second one. Good. So what's your outcome? Outcome is just 4. Yep. Good. We're equal to 3 in the second one, not the first one. So we're going to choose that one.
Oh, I kept thinking that each one was like individual and it didn't go that makes
No,
sense.
yeah, you could use the rule more than once. Who you want, you dream?
Taylor.
Taylor. How about f of 4? Second one again. So what's my outcome? Just 4 again. Yep. Popcorn.
I get 4. 4. Because it falls in the second one.
It doesn't. Because the second one's not equal to 7. Where can I be equal to 7?
Wait, which one are we on?
F of 7.
Oh, I thought I was doing F4. My bad.
Oh.
Oh, yeah.
Okay, we'll do F of 7.
Yeah, that's the last one.
So which one are we going to plug it into?
The last one.
The last one. So what is 2 times 7 plus 10?
24.
There it is. Yep. Sorry, we moved ahead without telling you. Yes. Good. Evaluating? We okay with it?
Yep.
So before you plug it in, just make sure you figure out where you're allowed to plug it into. Okay? I'm going to show you a visual on this one also. If I were to graph this, I would have a negative line over here. This is going to be real rough. A negative line, open circle. Then I would have a solid piece. Oh, that would be open. Like that. And then a line looking like this. Okay? Where this was 3 and that's 7. Okay? So what you're doing is you're finding x, y values. So if I have an x value of -7, okay, and I want to find the y value, the function it's going to end up being on is that line on this side. Does that make sense? If I plug in an x value of 3 or 4, which are right here, right, 3 and 4, their y values are going to both be on that line going across on 4. You're finding a point on the graph and telling me what piece it's on. If I plugged in 7, found the y value, well, it's not included here, but it is here. That y value is 24. So you're finding points on a graph. And those points exist on those certain pieces. Okay. This one is same thing we were just doing, but I've actually given you domains and ranges to match up with. Okay. I didn't give you x and y's. I gave you domain and range. What's range?
The y value.
Range is y. Domain is x. Good. Which one is your input? Your domain. What's your output? Your range. Okay? So you're inputting your domain values to seeing what the output is of my range. And you're going to draw lines and connect them. Okay? We have a new functions. We have x cubed minus 1. That's only if my x is less than or equal to 2. Then we have 6. Only if the x value is in between 2 and 5, not equal to them. And then we have 3 minus 4x, only if the x value is equal to or bigger than 5. All right, Graham, what'd you do? What'd you get when you plugged in -1? What'd you get out of it? Did I just call you Graham?
Yeah, Graham, what's up?
Graham Cook.
I have Graham Cook in my other class. I apologize. I do teach him. I'm sorry. What do you get when you plug in -1?
-2.
You get a -2 out of it. You may popcorn to somebody else. Jacob, how about when we plug in 2?
Which Jacob?
Oh,
Yeah, which
I
one?
assumed this one.
Which one?
Which one?
Is the top one?
What?
We're plugging it into the top one. You're right. So what is 2 cubed minus 1?
15.
2 cubed is what? 2 times 2 times 2. All right. And then what's 8 minus 1?
7.
7. So 2 goes to 7. All right, popcorn.
Okay. 3.5. It's the second one.
Yep.
So it's just 6.
So it's just 6. Good. Because -3 is in between 2 and 5. Popcorn.
Langston.
Not to Graham Cook. He's not here.
Langston.
Langston, what about 5?
Plugging it in.
Which one are you plugging it into?
The second one. No, the third one.
Yep, the third one. Good. We can be equal to 5 on the third one.
You get -17.
Yes. Good.
And the last one you get 21.
Right, it's kind of right there in our face. Which one did we get to plug it into, though? The bottom one again. So it becomes 3 minus 24. We get -21. We good? So we can use a function more than once, right? That's fine. Because the function is your y. You can repeat your y's, right? What we cannot repeat is my x. So for it to say a function, your x cannot get plugged into 2 different functions. That would be using your x twice. All right? One more. Looking at this lovely piecewise graph. I like this piecewise graph because a lot of these have started and ended at the same x value. This one, my line, it stops at what? -1? And then there's a big old jump to 2 where my curve one starts. So that's going to happen. There might be a big gap in the middle. They don't have to start and stop at the same x value. All right, looking at this, the function is decreasing over the interval -infinity to -1.
No.
So true or false. So we've been doing inequality function, right? So -infinity to -1, is that less than or bigger than 1?
That's less than.
It's less than. So the function is the function decreasing
Yes.
where x is less than -1.
So it's true.
Yes, that one is true. -infinity to -1 is the same thing as saying x is less than -1. All right, is this function continuous?
No. It's
No,
broken.
why not?
It's broken.
It's broken. And there's a hole. The increasing interval is linear.
No.
No, which one's my increasing interval? The curved, right? The nonlinear one. Good. The domain of the increasing piece, which we just said was the curved one, right? Is from 1 to infinity. No, why not? It's 2 to infinity. 2 to infinity. There we go. The range of my function is from -infinity to -1, and then 1 to infinity. No. It's from 1 to infinity. The lowest y is actually it's -1, excuse me. My lowest y is -1, not included, all the way up to positive infinity. So y's have to be bigger, have to be greater than -1. If that was -infinity to -1, and then it was 2 to infinity, that's technically my domain of this function. Because of that gap, it shows you the domain of the two different pieces. F of -1 equals -1. So if I input -1 for an x, do I get a -1 for my output of y?
No.
Olivia Bell, though, is saying no. And I agree with her. Why not?
Because it's an open.
I think you were speaking for her. Yes. She was shaking her head no because it is an open dot at -1, -1. So that is not included. How what?
Because it doesn't run through it.
You input -1. If you find where is your x of -1, it's on the first line, right? You cannot plug in x of -1 and end up on the curve. It's impossible. How about f of 4? If I plug in x of 4,
Because it runs through it?
it's going to be, do I get a 5 out of it? Yeah, it's on my curve. 4, 5 is a dot, and it's on my curve. That one is good to go. Easy. So today I'm giving you functions. I'm giving you graphs. Tomorrow you're going to have to make them. Tomorrow we'll focus on I give you the function and you draw the graph. And then Monday I'll probably give you the graph and you have to make the function.
What's our homework?
All right, I'm gonna give you your homework worksheet right now. Hopefully, I have enough. Work on it today. You cannot pack up unless you have a stamp or the bell rings. Got it? A stamp.